NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new.
It's clear that Webb represents the best of NASA.
40 light-years away, nestled around a dim red dwarf star, lies one of the most intriguing planetary systems ever discovered, TRAPPIST-1. Unlike our own solar system, where planets spread across vast distances, TRAPPIST-1's 7 Earth-sized worlds are packed into orbits so compact that they could all fit within Mercury's path around the Sun. At first glance, such proximity to their host star might seem hostile to life, yet astronomers believe that some of these planets could harbor conditions suitable for habitability. But wait, did James Webb find an atmosphere near TRAPPIST-1? Well, let's answer this and much more today. The TRAPPIST-1 system. The TRAPPIST-1 system comprises of a compact arrangement of Earth-sized worlds orbiting an ultra-cool red dwarf. At the heart of this system is TRAPPIST-1, a star with only about 12% of the Sun's radius and a mere 9% of its mass, making it barely larger than Jupiter. Its surface temperature hovers around 227 degrees Celsius or 440 degrees Fahrenheit, classifying it as a low luminosity, low energy output star. Unlike the Sun, which radiates high levels of visible and ultraviolet light, TRAPPIST-1 primarily emits infrared radiation, which has profound implications for the planetary climates and atmospheres of its orbiting worlds. What makes the TRAPPIST-1 system particularly fascinating is its unique planetary architecture. All 7 of its known exoplanets are Earth-sized, with diameters ranging between 0.76 and 1.13 times that of Earth. Despite their physical similarities, these worlds are packed into orbits so tight that the entire system could fit well within Mercury's orbit around the Sun. But despite this, they may harbor life. Yes, life may indeed have finally found a way. The way these planets are packed allows for strong gravitational interactions, leading to orbital resonances. This is when planets tug on one another in predictable ways, affecting their orbits and rotation states. These interactions, combined with transit timing variations, which are slight changes in the timing of a planet's transit across its star, caused by gravitational interactions with other nearby planets, enable scientists to determine the masses and densities of the planets with remarkable precision. Data suggests that these planets are mostly rocky, with little to no hydrogen-dominated atmospheres, making them prime candidates for studies on potential habitability. Among the 7, 3 planets, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, reside within the system's habitable zone, the so-called Goldilocks zone, where conditions might allow for liquid water to exist on the surface. However, the likelihood of surface water also depends on atmospheric composition, greenhouse effects, and stellar radiation. However, TRAPPIST-1's extreme age, estimated at around 7.6 billion years, makes it older than our solar system. This has raised intriguing possibilities. With such an extended timescale, any potential biological processes could have had far longer to develop than those on Earth. Yet, this longevity also presents challenges, as older red dwarfs can exhibit prolonged stellar activity, including intense stellar flares and ionizing radiation, which might strip away planetary atmospheres or alter their chemical compositions. The TRAPPIST-1 planets, due to their close orbits, are likely tidally locked, meaning one hemisphere permanently faces the star, while the other remains in perpetual darkness. This could create extreme climate zones, with a scorching day side and a frigid night side, unless atmospheric circulation helps distribute heat more evenly. Studies suggest that certain atmospheric conditions, particularly thick carbon dioxide-rich atmospheres, could mitigate these extremes, potentially making some planets more Earth-like in their climate stability. So, could these planets host life? Well, let's get some context first. The role of atmospheres in habitability. The habitability of the TRAPPIST-1 planets is heavily influenced by the presence and composition of their atmospheres, which play a crucial role in determining surface conditions, temperature regulation, and the potential for liquid water. However, their close proximity to the ultra-cool red dwarf poses significant challenges for atmospheric retention. Intense stellar radiation and strong stellar winds could strip away lighter elements, particularly hydrogen and helium, leaving behind only dense secondary atmospheres, if any at all. Among the 7 planets, TRAPPIST-1e stands out as the most promising candidate for habitability, as it may have retained a secondary atmosphere rich in heavier molecules like carbon dioxide, nitrogen, and possibly even water vapor. If this atmosphere is dense enough to regulate heat distribution and protect against stellar activity, TRAPPIST-1e could host conditions suitable for life. Understanding these atmospheres requires advanced observational techniques, with astronomers employing cutting-edge space telescopes to probe the chemical compositions of these distant worlds. The Hubble Space Telescope was instrumental in early studies of the TRAPPIST-1 system using transmission spectroscopy to analyze starlight passing through planetary atmospheres. These observations ruled out thick hydrogen-dominated atmospheres for TRAPPIST-1b and TRAPPIST-1c, suggesting that, if they have atmospheres at all, they are likely composed of heavier gases rather than being mini-Neptunes with extensive hydrogen envelopes. The James Webb Space Telescope is now revolutionizing our understanding of the TRAPPIST-1 system by providing detailed infrared observations. By detecting specific absorption features in starlight as it filters through planetary atmospheres, JWST can identify key gases such as water vapor, carbon dioxide, and oxygen. Initial thermal emission studies have already revealed that some planets, like TRAPPIST-1b, likely lack substantial atmospheres, with secondary eclipse observations confirming it is a barren, airless rock. As JWST continues to study the system, upcoming data will shed light on whether any of the other planets, particularly TRAPPIST-1e, retain atmospheres capable of supporting liquid water. If some of these planets have indeed managed to retain substantial atmospheres despite the host star's high-energy radiation, it would significantly expand the potential for life-bearing worlds around low-mass stars. On the other hand, if most or all of these planets have been stripped of their atmospheres, it would raise serious concerns about the habitability of similar planetary systems throughout the galaxy. But wait, there's more. Challenges of red dwarf stars for habitability. Red dwarfs are the most common stars in the universe, offering an abundance of planetary systems, yet their harsh stellar environments pose serious challenges for life as we know it. In their early evolutionary stages, red dwarfs like TRAPPIST-1 undergo an extended pre-main sequence phase that can last for approximately 100 million years, during which they are significantly more luminous than in their later stable phase. This prolonged period of high-energy radiation results in extreme ultraviolet and X-ray exposure for any orbiting planets, particularly those in the habitable zone, making it difficult for atmospheres to survive. One of the most severe threats to planetary atmospheres in red dwarf systems is hydrodynamic escape, a process driven by intense stellar radiation. As a young red dwarf bombards its planets with high-energy photons, atmospheric particles heat up, expand, and are gradually stripped away into space. This effect is particularly devastating for lighter gases such as hydrogen and helium, but it can also lead to the depletion of heavier molecules like carbon dioxide and water vapor over extended periods. Even if a planet initially formed with a thick, life-supporting atmosphere, sustained radiation exposure could erode it down to a barren, airless surface unless a significant replenishment mechanism, such as volcanic outgassing or cometary impacts, counteracts these losses. Adding to the instability, red dwarfs are notorious for their frequent and violent stellar flares, which can release bursts of high-energy radiation and charged particles. These flares, sometimes thousands of times more powerful than those from the Sun, have the potential to ionize upper atmospheres and drive away critical atmospheric components through stellar wind stripping. Planets that lack strong magnetic fields are especially vulnerable, as they have no protective barrier to deflect these charged particles. If a planet like TRAPPIST-1e orbits within the habitable zone but lacks a sufficient magnetosphere, its atmosphere may be continuously eroded by these stellar winds, further diminishing its potential for habitability. Despite these challenges, some scientists argue that certain planetary conditions could mitigate these effects. A planet with a sufficiently massive atmosphere, rich in heavier gases like nitrogen or carbon dioxide, might be able to resist complete atmospheric loss. Likewise, a strong planetary magnetic field, similar to Earth's, could shield against the worst effects of stellar radiation. However, given the compact orbits of the TRAPPIST-1 planets, where all 7 worlds are packed within a distance smaller than Mercury's orbit around the Sun. Sustaining such protective conditions would require exceptional geological or atmospheric resilience. So, what can we expect in this situation? Why TRAPPIST-1e might retain an atmosphere? Despite the extreme stellar conditions imposed by its red dwarf host, TRAPPIST-1e may have retained an atmosphere. One of the key reasons for this is the possibility that the planet initially formed with a thick primordial hydrogen atmosphere which, over billions of years, may have been gradually stripped away due to stellar radiation. As this early hydrogen envelope dissipated, TRAPPIST-1e likely developed a secondary atmosphere through volcanic outgassing, a process in which internal geological activity released gases such as carbon dioxide and water vapor from its interior. This transition is crucial because a secondary atmosphere composed of heavier molecules is more resistant to complete erosion compared to the light hydrogen atmospheres that many exoplanets lose in their early stages. Another critical factor contributing to TRAPPIST-1e's potential atmospheric retention is its distance from the host star. While still in a compact orbit, TRAPPIST-1e is farther from the intense radiation zone compared to inner planets like TRAPPIST-1b. TRAPPIST-1b, located closest to the star, has almost certainly lost its atmosphere due to the relentless bombardment of stellar wind, X-rays, and ultraviolet radiation. The reduced exposure to extreme radiation at TRAPPIST-1e's orbit may have slowed the rate of atmospheric loss, allowing it to retain a more substantial atmosphere over time. Additionally, if TRAPPIST-1e possesses a strong magnetic field, it could provide an additional layer of protection against atmospheric stripping by deflecting charged particles from the stellar wind. Outgassing from early magma oceans on TRAPPIST-1e could have played a fundamental role in replenishing its atmosphere with greenhouse gases such as carbon dioxide, which would help regulate surface temperatures and maintain liquid water if conditions are right. Unlike gas giant planets, which retain hydrogen and helium, rocky exoplanets like TRAPPIST-1e depend on internal geological activity to sustain their atmospheres over geological timescales. If volcanic activity has continued over billions of years, it could have provided an ongoing source of carbon dioxide, strengthening the planet's atmospheric stability and making it more resistant to gradual erosion. But to see is to believe. For that, we must wait. If TRAPPIST-1e is found to have a significant atmosphere, it would suggest that Earth-sized planets orbiting red dwarfs may be more resilient to harsh stellar environments than previously believed. Conversely, if JWST detects little or no atmosphere, it would reinforce concerns that red dwarf planets may generally be inhospitable for life. For the sake of argument, let's assume the first possibility as true. Can we then finally make first contact with an alien life form? And even more importantly, why haven't we done so already? Where is everybody? This question is not new. In fact, this is precisely what physicist Enrico Fermi pondered in the 1950s. With billions of Earth-like exoplanets scattered across the galaxy, the sheer probability suggests that intelligent life should have emerged multiple times. Yet, despite decades of radio signals, space probes, and SETI, or search for extraterrestrial intelligence efforts, we have found nothing but silence. Moreover, the Drake equation, developed by astronomer Frank Drake in 1961, attempts to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way. The equation factors in variables such as the rate of star formation, the fraction of planets capable of supporting life, and the likelihood of technological advancement. While the equation provides a framework for estimating the probability of extraterrestrial intelligence, it does not address why we have yet to detect any signals or evidence of alien civilizations. So, how come there is only silence? Some argue that intelligent life may be exceedingly rare, with civilizations either self-destructing before achieving interstellar capabilities or existing at such vast distances that communication is impractical. Others propose a more unsettling possibility, that civilizations are intentionally silent because broadcasting their existence could lead to catastrophic consequences. The dark forest hypothesis, introduced by science fiction writer Liu Cixin in his 2008 novel The Dark Forest, presents a chilling perspective on why the cosmos appears so eerily quiet. The hypothesis suggests that all civilizations in the universe are like hunters in a dark forest, each moving cautiously and avoiding detection to ensure their survival. The fundamental assumption is that any contact between two civilizations carries the risk of existential threat. Since it is impossible to know the intentions of an alien civilization, the safest course of action is to remain undetected. If a civilization reveals itself, it risks being perceived as a future competitor for resources or as a potential threat, prompting more advanced civilizations to eliminate them preemptively before they become dangerous. The underlying idea is that in an interstellar environment, civilizations cannot easily assess one another's motivations or long-term strategies. Even if one civilization intends peace, it cannot be certain that others will interpret its actions in the same way. The logical conclusion, therefore, is that any rational civilization will assume the worst and take measures to either hide or eliminate potential threats before they escalate. This mirrors historical patterns on Earth, where uncertainty between competing groups often leads to preemptive aggression. Another factor reinforcing this hypothesis is the technological explosion, the idea that once a civilization reaches a certain level of technological advancement, its power could increase exponentially in a short time. A more advanced civilization might recognize that even a seemingly harmless, less developed species could eventually become a serious competitor. This raises the possibility that some advanced alien civilizations might adopt a preemptive strike policy, eliminating emerging technological threats before they become too powerful to control. Despite these concerns, some scientists argue that remaining silent out of fear may be an irrational response. Douglas Vakoch, an astrobiologist and former director of the SETI Institute, advocates for continued efforts to make contact, arguing that a truly hostile alien civilization would have likely attacked Earth long before we became technologically advanced enough to detect them. He suggests that the absence of an attack indicates either that no such civilizations exist or that they may be benign. Furthermore, some counterarguments propose that not all civilizations are inherently aggressive. Some may be cooperative, curious, or even willing to engage in mutually beneficial exchanges. But there are other possibilities too. Alternative explanations for the Fermi paradox. The Fermi paradox remains one of the greatest unanswered questions in modern science. And while the dark forest hypothesis presents one possible answer, it is far from the only explanation. Several alternative theories attempt to resolve this cosmic mystery, each offering a different perspective on why the universe appears so eerily quiet. One major factor could be the immense cosmic distances between stars and galaxies, which create significant barriers to communication and exploration. The scale of the universe is so vast that even if intelligent life exists, it may be too far away for us to detect or interact with it. Radio signals, our primary method of searching for extraterrestrial intelligence, take years, if not centuries, to travel between even the closest star systems. For example, Proxima Centauri, the closest known exoplanetary system, is 4.24 light-years away, meaning any signal sent there would take over 4 years to arrive. For more distant exoplanets, signals could take thousands or even millions of years to reach us. If civilizations are attempting to communicate, their signals may have simply not yet reached Earth, or vice versa. Another possibility is that intelligent life is far rarer than we assume. While microbial life may be common throughout the cosmos, the emergence of complex, intelligent civilizations could be extraordinarily rare. This theory aligns with the idea of the Great Filter, which suggests that there is a critical stage in evolution that most life forms fail to pass. This filter could occur at any point. Perhaps the transition from single-celled to multicellular organisms is highly improbable, or perhaps most civilizations self-destruct before reaching a stage where they can engage in interstellar communication. If the Great Filter lies ahead of us, it implies that civilizations may be doomed to eventual extinction, whether through nuclear war, ecological collapse, or uncontrollable artificial intelligence. If the Great Filter is behind us, however, it means that Earth has already passed an incredibly difficult evolutionary hurdle, making humanity one of the few, if not the only, intelligent species to have survived. Additionally, it is possible that alien civilizations do exist, but are simply uninterested in communicating with us. They may have advanced beyond the need for interstellar exploration or communication, instead choosing to remain isolated within their own technological spheres. Some may have reached a post-biological state, existing purely as machine-based intelligence that has no interest in engaging with primitive biological life like humans. Others may be following a prime directive-like philosophy, choosing not to interfere with developing civilizations to allow them to evolve naturally. Another explanation is that we are looking in the wrong way. Our searches for extraterrestrial intelligence primarily rely on radio waves, assuming that other civilizations would use the same method of communication. However, a sufficiently advanced species might use entirely different forms of communication, such as quantum entanglement, neutrino-based messaging, or technology beyond our current understanding. If alien civilizations do not use radio waves, or if they have already switched to more advanced means of communication long before humans developed radio astronomy, then we may simply be missing their signals altogether. Finally, some scientists suggest that we may be living in a cosmic zoo, where more advanced civilizations have deliberately chosen to keep Earth in a state of isolation. This idea, known as the zoo hypothesis, suggests that extraterrestrials may be observing us, much like how humans observe wildlife in nature reserves. If such a system exists, they may have strict rules preventing direct contact until humanity reaches a certain level of technological or social maturity. Alternatively, the simulation hypothesis proposes that the universe as we perceive it may be a highly advanced simulation, meaning that extraterrestrial life is either non-existent or deliberately hidden by the creators of the simulation. Ultimately, the lack of evidence for extraterrestrial life leaves all these hypotheses unconfirmed. The Fermi paradox continues to challenge scientists, philosophers, and astronomers, pushing us to rethink our assumptions about the nature of life in the universe. Perhaps the answer is closer to home than we think. Earth's role in the cosmic landscape, often viewed as a tranquil oasis in the vast and silent cosmos, Earth is a planet teeming with life, protected by unseen forces that maintain its delicate balance. Among these, the Earth's magnetic field shields life from the harsh conditions of space. Without this protective barrier, the planet would be exposed to relentless solar winds and cosmic radiation, which could strip away the atmosphere and render Earth uninhabitable, much like Mars. The magnetic field acts as a deflector, redirecting charged particles away from the planet's surface, and ensuring the stability necessary for the evolution and survival of complex organisms. This protective shield is generated deep within the planet through a process known as the geodynamo effect, driven by the movement of molten iron and nickel in Earth's outer core. The continuous churning of these metals, combined with the Coriolis effect, caused by Earth's rotation, creates electric currents, which in turn produce the powerful magnetic field that extends far into space. Beyond merely safeguarding life, this magnetic field plays a pivotal role in navigation, guiding everything from migratory birds to human explorers who have relied on compasses for centuries. However, Earth's magnetic field is not static. It undergoes periodic geomagnetic reversals, where the magnetic poles switch places. Evidence of these reversals is preserved in the geological record, particularly in volcanic rocks and oceanic magnetic striping, which capture the direction of Earth's magnetic field as lava cools. Scientists have identified that these pole reversals have occurred hundreds of times over millions of years, with the most recent full reversal, the Brunhes-Matuyama reversal, taking place around 781,000 years ago. Unlike clockwork events, these reversals happen at irregular intervals, ranging from tens of thousands to millions of years, making their timing unpredictable. Recent satellite observations indicate that Earth's magnetic field is weakening, raising questions about the possibility of another reversal in the near future. One particularly concerning sign is the rapid drift of the North Magnetic Pole, which has been shifting towards Siberia at an increasing pace. Additionally, scientists have identified an expanding weak spot in the field, known as the South Atlantic Anomaly. This region, stretching from South America to the southern Atlantic Ocean, is an area where the magnetic field strength is significantly lower, allowing higher levels of radiation to penetrate the atmosphere. This poses risks to spacecraft, satellites, and even power grids. as increased exposure to cosmic radiation can damage sensitive electronic systems and interfere with communications. To understand the long-term implications of these geomagnetic changes, scientists rely on data from satellites and ground-based observatories. The European Space Agency's SWARM mission, a trio of satellites dedicated to studying Earth's magnetic field, provides crucial insights into its strength, direction, and anomalies. These observations help researchers predict potential geomagnetic reversals and assess their possible impacts on life and technology. While the consequences of a full reversal remain uncertain, some scientists speculate that it could weaken Earth's ability to shield against radiation, increasing the likelihood of power grid failures, disruptions in GPS navigation, and heightened radiation exposure for both humans and electronic systems. Despite the uncertainty, history suggests that geomagnetic reversals are natural events that Earth has endured many times before. Understanding Earth's magnetic field highlights the fragile yet remarkable conditions that have allowed life to flourish in this cosmic oasis. This insight is crucial when studying exoplanets like those in the TRAPPIST-1 system, where the presence or absence of a magnetic field could determine habitability. Planets such as TRAPPIST-1e, which may retain an atmosphere, would require a strong magnetic field to prevent atmospheric erosion from intense stellar radiation. Without this protective shield, even a potentially habitable world could lose its water and atmosphere over time, much like Mars did in our own solar system. As researchers use the James Webb Space Telescope to analyze these distant worlds, understanding their magnetic environments will be key to assessing their potential to sustain life. The search for magnetic fields beyond Earth. Located just 12 light-years away, the star YZ Ceti emits a mysterious radio signal. This signal, detected by scientists, suggests that a rocky exoplanet orbiting YZ Ceti may possess a magnetic field similar to Earth's, a crucial factor in determining its habitability. Radio signals can originate from natural celestial bodies, artificial satellites, or deep space objects, providing astronomers with data about distant worlds. Advanced radio telescopes, such as the Very Large Array and the now-defunct Arecibo Observatory, have played pivotal roles in detecting and analyzing these signals. These telescopes rely on sophisticated algorithms to filter out cosmic noise and identify patterns that may indicate planetary activity, interactions between celestial objects, or even signs of extraterrestrial intelligence. Beyond astronomical research, radio waves have practical applications on Earth, powering technologies such as GPS navigation, weather forecasting, and Earth observation systems. The YZ Ceti system, home to at least 3 known exoplanets, is centered around a small, cool red dwarf. Among these planets, YZ Ceti b stands out due to its tight orbit, completing a full revolution around its star in just 1.6 Earth days. This extreme proximity means that any magnetic field it possesses would be subjected to intense interactions with the star's own magnetic activity. Scientists from Bucknell University recently detected a repeating radio signal in the 2 to 4 GHz range, suggesting a dynamic relationship between YZ Ceti b's magnetic field and its host star. The significance of this discovery extends beyond a single exoplanet. Magnetic fields are critical in shaping planetary environments, as they serve as protective shields against stellar radiation and atmospheric erosion. On Earth, the magnetic field deflects solar winds, preventing them from stripping away the atmosphere and allowing conditions for life to persist. If exoplanets such as YZ Ceti b also possess strong magnetic fields, it raises intriguing possibilities about their potential to harbor life. Furthermore, magnetic fields influence radio signals in several ways, including deflection, polarization changes, and frequency shifts. These alterations provide scientists with valuable insights into the properties of distant planetary magnetic fields, offering a new method for indirectly detecting exoplanetary magnetospheres. However, magnetic interference can also distort signals, making it challenging to distinguish planetary emissions from other cosmic noise. In any case, future observations using next-generation instruments such as the Square Kilometre Array and James Webb Space Telescope may confirm whether such fields are common among rocky exoplanets, and, ultimately, whether they could create environments where life might thrive beyond our solar system. Well, for now, we can only wait for more information and insights. These too will come in time. The future of space research and exoplanet studies. With over 5,500 confirmed exoplanets catalogued and thousands more awaiting verification, astronomers are rapidly uncovering the diversity of worlds beyond our solar system. From hot Jupiters to Earth-like exoplanets within habitable zones, each new discovery refines our understanding of planetary formation, atmospheric composition, and potential habitability. One of the most promising areas of research lies in the detection of exoplanetary magnetic fields, as demonstrated by the recent findings from YZ Ceti b. The presence of such fields could indicate atmospheric stability and long-term habitability, key factors in the search for alien life. Future missions, such as NASA's Habitable Worlds Observatory and the European Space Agency's Aerial Telescope, will allow scientists to study exoplanetary atmospheres in detail, searching for biosignatures like oxygen, methane, and water vapor. Meanwhile, radio telescopes like the Square Kilometre Array will enhance our ability to detect faint electromagnetic signals, potentially identifying more magnetized exoplanets and their interactions with host stars. Beyond exoplanet studies, upcoming deep space exploration missions will push the boundaries of human knowledge. NASA's Artemis program is set to return humans to the Moon by the late 2020s, laying the groundwork for a sustained presence and eventual crewed missions to Mars. The James Webb Space Telescope continues to unveil the secrets of the early universe, detecting galaxies formed over 13 billion years ago, offering clues about cosmic evolution. At the same time, next-generation observatories like the Nancy Grace Roman Space Telescope will focus on exoplanet detection and dark matter research, deepening our understanding of the universe's fundamental forces. Perhaps the most exciting prospect is the increasing role of artificial intelligence and machine learning in astrophysical studies. These technologies are revolutionizing how scientists analyze vast datasets, from automated exoplanet detection to the interpretation of complex astronomical phenomena. With AI-driven pattern recognition, future space missions may identify Earth-like planets faster and refine methods for detecting extraterrestrial life. Despite the immense distances and challenges associated with interstellar exploration, the progress in space science brings hope that humanity will one day bridge the cosmic divide. With each new discovery, whether a magnetized exoplanet, a habitable world, or an unidentified signal from deep space, we move closer to answering the profound question: are we alone in the universe? The future of space exploration is filled with promise, and with continued innovation, collaboration, and curiosity, the next great discovery may be just beyond the horizon. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.